Fine. So we have now in the solution C2H5OH. So now this electrons on the OH atoms will now attack on the plus charge of the carbon. Alright, so we are left with OH. We had a C over here, CH2 actually, to be very specific. O, H, C2, H5. And now this oxygen has the positive charge. Alright, when this oxygen atom attacks this carbocation, the plus charge is shifted to the oxygen atom. Alright, I hope you would understand this simple reaction. Okay, now what happens is that since this was an acid catalyzed reaction, an H plus was added and now an H plus needs to be removed. Alright, now H plus will be removed. It's very evident that O, since it has a positive charge, will now try to break a bond. Alright, and one H plus has to be removed. So this H plus is removed from the substrate. So we are now left with C, O, C2, H5, and over here OH. Okay, fine then. I hope you understand the basics of this reaction. What is happening when an epoxide reacts with C2H5OH, a base, in presence of an acid. Alright, I hope you understand this. I am taking up one more example for your suitability, for you to understand this reaction better. Alright, I am taking out one more example. Okay, so let me be very specific that this is the best part. This is the heart of the reactions of ethers. If you understand these kind of reactions, you are almost done with the chapter of ethers. So please take this lectures very seriously. Try to understand the basics of this reaction so that the ether chapter that we have is becomes very simple to you. Okay, so I take up another example of a cyclic ether attack on cyclic ether reaction. Alright, in this case I haven't taken a simple epoxide. Methyl group is attached to this carbon. Okay, so now what happens? C2H5OH, again we have C2H5OH in presence of the H plus ion. Now again H plus ion attacks on the O oxygen atom. We have this. So now the O, okay, let me modify the question. I change the methyl group from this position to this position. Okay, it's not a very big change. Alright, okay, I change the methyl group. Okay, alright. So we have a plus charged oxygen atom which is not stable. It will try to break one of its 3 bonds heterolytically and take up the electrons of the bond. Alright, so now we have two choices, either to break this bond or to break this bond. Alright, I'll break both the bonds for you, and it's time for you to decide that which bond will be broken, which step is to be followed. Alright, so I'll first break up this one and I'll then break up this one. So the product that we obtained from A, I'm writing out here. Alright, when I break this bond, what do I get? I get and a plus charge over here. I think you get this, because when this bond is heterolytically cleaved, the electrons go to this oxygen atom. So this oxygen atom is now neutral. Now this carbon atom, because this was a heterolytic cleavage, has acquired a positive charge. This is very simple. Alright, now what if the B bond is cleaved? Alright, so I'm rubbing the part of A so that this is clear to you. Alright, now what if this B bond cleaves? I cleaved this B bond heterolytically. These electrons go to oxygen. Alright, now what happens? we are left with a plus charge on this carbon. Alright, now please look into the question, look into these two products and decide which one is more stable. This is very simple. This involves the basic knowledge of carbocations. This is very simple. So I hope you understand. This is a 1 degree carbocation. This is a 2 degree carbocation. Which is stable? Obviously 2 degree carbocation is more stable because this has more number of hyperconjugable hydrogen atoms, more number of no bonding resonance structures than this, plus this is favored by inductive effect. So 2 degree carbocation is more stable than 1 degree carbocation. Alright, if you do not understand this concept, I would suggest you to go back to the carbocation lecture part and go through the nits and grits of this carbocation stuff, so that you get a better idea of what is happening over here. Why this product, I'll take up this product rather than this. Why this is less stable than this product. Alright, so I came up to the conclusion that this compound is more stable, and therefore this will be favored, and therefore the path A will be followed rather than following path B. Alright, so we have this carbocation. Now again, I'm rubbing off the initial part of the question. Now we have C2H5OH with us. Alright, now this attacks at this plus charged carbon or the carbocation. So we are left with O C2H5. Okay, I think you're getting my point, that when C2H5OH or the alcohol was reacted in presence of an acid, the reaction is governed by the formation of a carbocation. Alright, I hope you are getting this. A carbocation is being formed. So every reaction product will be governed by the stability of the carbocation. Right, so this is SN1 reaction. As you know, in case of substitution nucleophilic unimolecular reaction, we have a carbocationic intermediate. We are getting a carbocationic intermediate over here. This is SN1 reaction. So this is governed by carbocation stability. Right, this was like acid catalyzed, so one H needs to be removed. Okay, so we are left with O ET. C2H5 is replaced by ET. Alright, so I hope you are getting my point. Hope you are getting the fundamentals of how cyclic ethers react with acids or nucleophiles in general in presence of acids. First, let me quickly write it down for you. First, the cyclic ether is being attacked by H+. The H+ attacks this O. We have this. Now the breakage of the bond, the heterolytic cleavage of the bond, depends upon the stability of the carbocation. That bond will be cleaved, that leads to the formation of a more stable carbocation. This step is the most important and the only important step, maybe I can say, in this reaction. Everything else is very simple. Everything else is just the substitution nucleophilic part. Alright, so the formation of carbocation, the formation of stable carbocation is the most important part. Okay, in this case both were equivalent, so I need not take into account which bond was to cleave. But if there was the case was like this, so rather than the cleavage of this left bond, this right bond would have cleaved, which would have led to the formation of a more stable carbocation. Then C2H5OH attacks as the nucleophile. Alright, so we are left with this OETH again. Now, as it was a acid catalyzed reaction, one H plus is removed and we get this as the product. Alright, so I hope you get my point and hope you understand the fundamentals of how a cyclic ether reacts with a nucleophile in presence of an acid. Let me tell you that the case is just the opposite when a nucleophile attacks a cyclic ether in presence of a base. This reaction was SN1 in case of acid catalyzed, but when it is base catalyzed, the reaction is SN2. Alright,